welcome to the deep dive.
Yeah.
Today, we are strapping in for a really rapid, but I think comprehensive journey through the fundamentals of computer science.
Exactly.
Our mission is pretty simple.
Yeah.
Take this dense foundational course material, the core concepts, the terminology, and just pull out the critical knowledge nuggets.
Right. Think of it as a shortcut.
Yeah, an accelerated shortcut to understanding the bedrock of all modern computing.
And we're not just reading definitions. We're trying to get to the consequences of those definitions. We're going to distill everything from, how a single number is stored all the way up to how massive software projects get managed.
I love that.
Yeah.
Okay, let's start with the machine scripts then, in this sort of invisible world of information encoding.
Mm-hmm.
So when a computer stores a signed integer, a positive or negative number, it has to use one of its bits just for the sign.
Right. And our sources point to two main ways of handling this. The older way, sign and magnitude, and the modern way, 2's complement.
And what's so interesting is how engineers solved what is, well, a really fundamental and almost silly problem.
It really is. If you use the old sign and magnitude method, you end up with two different versions of 0.
Right, a positive 0 and a negative 0.
Exactly. You've got 000 for +0 and 1000 for -0. And that redundancy, it's not just inefficient, it actually makes the circuitry for doing math way more complicated.
And this is where the elegance of 2's complement just completely takes over. It's what basically every modern computer uses now.
It is, and it's all about streamlining the math.
Right.
By defining negative numbers in a very clever way, you flip the bits and add 2's complement gets you down to just one single representation for 0.
Just all zeros.
Just all zeros. And that massively simplifies the physical logic gates in the processor. And as a nice little side effect, because you got rid of that redundant -0, you actually make room for one extra negative value. It's just a cleaner solution all around.
It's amazing how much thought goes into just making sure 0 is 0.
Yeah.
Okay, let's pivot from math to text. We need to talk about the difference between the binary codes for arithmetic and the character codes we use for, text documents or what you see on screen.
They're totally separate things. When you're talking text, you're talking about something like ASCII, the original 7-bit standard.
Which was great, but
Very limited.
Oh,
It mostly just covered English characters, numbers, symbols. But the world is obviously a lot bigger than 7 bits.
way bigger. And that limitation is exactly why we needed Unicode.
Exactly. Unicode was designed to represent basically any possible text character in code form. From emojis to, Mandarin characters, everything gets a unique number. It's the standard for a truly global internet.
Okay, another data type, images. We always hear these two terms thrown around, vector and bitmap. If you're designing a logo, you use one. If you take a photo, you use the other. What's the real difference in how they're stored?
It all comes down to scalability. A bitmap image, like a photo from your camera, is just a big two-dimensional grid of colored dots, pixels.
So if you zoom in too far,
You see the squares, the quality just falls apart, you get that jagged, pixelated look because the dimensions are totally fixed.
and this is where vector graphics are so interesting because they solve that exact problem.
They do. A vector graphic doesn't store pixels at all. It stores a drawing list, a set of mathematical instructions.
So not 1,000 blue dots,
But a circle centered at position X, Y, with radius R filled with this color. And because it's just a formula, you can scale it to the size of a building and it will be perfectly crisp. No distortion.
So photos are bitmaps, logos and fonts are vectors.
That's the general rule, yeah.
Okay, before we move on to how this data gets processed,
Yeah.
let's quickly touch on compression. Lossless versus lossy.
Right, the two basic ways to shrink a file. With lossless compression, you reduce the file size, but you lose 0 information. The original file can be recovered perfectly, bit for bit.
Which you would absolutely need for a text document or a program.
You have to have it. You can't lose a single character. Think of a zip file, but then you have the trade-off.
Lossy compression.
Right. With lossy, you reduce the file size by throwing away some information forever. You can't get the original back. We accept this for things like streaming video or MP3s because our eyes and ears, they often can't even perceive what's missing.
And the bandwidth savings are huge. Okay, so we've encoded the data. Now let's move from the bytes to the brain that processes them, the von Neumann model.
This is the absolute foundation of modern computing, developed way back in the 1940s. It describes a processor, the CPU, that has direct access to a single block of memory.
And that memory holds both the data and the program instructions.
That's the key insight. Instructions could be treated just like data.
And the heart of it all is the fetch-execute cycle. When I first learned this, it just felt like a list of acronyms.
Oh yeah, PC, MAR, MDR, CIR. It's easy to get lost. But if you think of it as a process, it makes perfect sense.
So let's focus on that fetch stage. How does the CPU know what to grab next?
Well, think of the CPU as a hyper-efficient librarian. The PC, the program counter, holds the address of the next instruction it needs.
Like a page number.
Exactly. It sends that page number to the MR, the memory address register, which then acts like a pointer, going directly to that spot in memory.
When the instruction or the data comes back from memory.
It does. It gets held temporarily in the MDR, the memory data register. And once it's fully fetched, it's moved into the CIR, the current instruction register, to actually be decoded and executed.
And that dance PC to MER, memory to MDR, MDR to CIR that just repeats millions of times a second.
That's the engine of the whole machine.
Okay, moving from physical hardware to pure logic, we get to Boolean algebra.
This is where we define complex problems using simple statements that can only be true or false.
Which is critical for digital circuits.
It is, because in Boolean algebra, 1 is true, 0 is false. And even symbols like the plus sign take on a new meaning. Here, it means the logical operator, or OR.
These logical expressions can get incredibly complex, which means the circuits get complex. So how do engineers simplify them?
They need a good visual tool, and that's where kernel maps, or K-maps, come in. Instead of wrestling with long strings of algebra, a K-map lets you visually spot patterns and group logical terms together.
So you can take a really long expression
with maybe 5 or 6 parts and simplify it down to something much, much shorter but logically identical. And that directly means fewer physical components on a chip. It saves power, time, and money.
Right. It's about finding elegance and efficiency. Now let's zoom out from tiny circuits to the whole planet.
Okay.
We have to clarify 2 terms that everyone uses interchangeably. The Internet versus the World Wide Web.
Yes, this is such a key distinction. The Internet is the infrastructure. It's the physical and logical mesh of connected networks all over the world. It's the highway system.
And the WWW is the stuff on the highway system.
Precisely. The World Wide Web is an application, a massive collection of websites and documents linked together that runs on top of the Internet. You use the Internet to access the web.
So speaking of addresses on that network, how does every device in my house get on the global Internet without needing its own unique public address?
Ah, that's the magic of network address translation, or NAT.
Usually in my router, right?
Exactly. Inside your home network, your devices all have private internal IP addresses. NAT sits at the edge and acts like a receptionist. It takes all the requests from inside and maps them to a single public IP address that the outside world sees.
So it conserves addresses and adds a layer of security.
It does. It's a really clever piece of network design.
Okay, let's move into how software itself is structured. Before we write any code, we need a plan. What's an algorithm, really?
At its core, an algorithm is just a well-defined sequence of steps to do something. It's the recipe. And all these complex algorithms we have are built from just 4 basic constructs.
Let's see if I remember. Assignment, sequence?
Yep, giving a value to a variable and doing things one after another.
Selection, so like an ifs and else statement.
Right, a branching path. And the last one is repetition. Loops.
And how we organize these actions leads to different programming styles or paradigms. Let's talk about the big one. Procedural versus object-oriented.
This was a huge philosophical shift. Procedural programming is all about the action. You group statements into procedures and functions. The focus is on the verbs, the sequence of steps that manipulate data.
Like a strict set of instructions for building something.
Exactly. Whereas object-oriented programming, or OOP, shifts the focus to the entity, to the noun. It's about organizing code around objects, which model real-world things.
Like a customer object or an order object.
Right, and these objects bundle together both the data that describes them and the functions or methods that operate on that data. It makes managing huge projects much, much easier.
And just to briefly touch on another paradigm, what about declarative languages like Prolog?
So Prolog is about defining what a solution looks like, not the step-by-step how to get there. You give it a knowledge base of facts and rules, and then you ask it queries.
So when you use recursion there, you absolutely have to have
a base case, an explicit solution that stops the recursion. And you need a general case, which is the rule that keeps reducing the problem until it hits that base case. Without it, the program just searches forever.
Okay, that sets us up for the producer's toolkit. How does this conceptual code become a real program, and how do we know it works?
So, translation. Three main ways. First, for low-level stuff, you have the assembler. It converts assembly language mnemonics like ADD into raw machine code.
And the source material mentioned a two-pass method for this.
It did. The first pass just reads through the code to build a symbol table, sort of mapping everything out. The second pass then uses that map to generate the final executable code.
Okay, and then for high-level languages, we have the two that always get mixed up, the interpreter and the compiler.
The whole difference is timing. The interpreter reads and executes your code line by line on the fly.
And if it hits an error on line 50?
It just stops right there, which is great for debugging, but it's slower overall because it's translating as it goes.
Whereas the compiler takes the whole program in one big gulp.
Correct. It translates the entire source code into machine code before you run anything. The result is a fast, optimized program that can run all on its own.
But there's that famous middle ground we should mention.
Java.
Java, the special case. A Java compiler doesn't produce native machine code. It produces something called Java bytecode.
And that's what runs on the Java virtual machine, the JVM.
Exactly. So that same compiled bytecode can run on any computer, Windows, Mac, Linux, as long as it has the JVM installed. It's why they used to say, write once, run anywhere.
So once it's translated, we have to check that it actually works. Let's talk testing. First, black box testing.
Right. Black box testing is when you test the program based only on its specifications. You don't look at the code at all.
You're just checking if it does what it's supposed to do.
Precisely. And you have to use three kinds of test data: normal, valid data, abnormal or error-causing data, and most importantly, boundary data, testing the absolute edges, the minimums and maximums.
And the opposite approach, where you need to see everything, is white box testing. With white box, you are testing every single possible path and branch through the actual code. And if you're trying to debug that code manually, the essential tool is the trace table.
The dry run.
The dry run. You literally list out your variables on paper and track their values step by step as you walk through the algorithm. It's meticulous, but it's the ultimate way to find a logic error.
And when you scale all this up into a huge project, you need serious scheduling tools.
Absolutely. The sources highlight too. Gantt charts, which are those horizontal bar charts that visually show who is doing what and when.
And you can see where tasks overlap.
Exactly. And then for more analysis, you have the Peart chart.
This one is for finding bottlenecks. Right.
That's its main job. It shows activities and durations, but its real power is in identifying the critical path. That's the longest sequence of dependent tasks from start to finish. Any delay on that path delays the entire project.
So if we pull all of this together, it feels like a whole world of computing. From a single bit all the way to global networks, it all rests on these very precise structures, this strict logic, and just meticulous testing.
That's a perfect synthesis. It all builds on itself.
And that diligence is so important. Our source material brought up this just cautionary tale. The Ariane 5 rocket explosion in 1996.
It's a catastrophic failure.
$500 million, just gone. And it wasn't bad hardware. It was a single line of software, a single line of code trying to convert a 64-bit floating point number into a 16-bit integer.
And the number was just too big. It didn't fit. That created a data overflow, which crashed the guidance computer.
Which then triggered the rocket's self-destruct sequence. It's incredible. And it raises this really important question for all of us, doesn't it? How does knowing the mechanics of data representation, knowing the simple difference between 16 bits and 64 bits, which is the first thing we talked about today, how does that become a matter of such monumental consequence?
It reminds you that no matter how abstract the computer science gets, the consequences are always, eventually, physical.
So what seemingly small design decisions, something as fundamental as 2's complement or a single bit allocation, might already be influencing the technology you use every single day, just keeping it all running safely and efficiently. It's something to think about. Thanks for diving deep with us.